Mixtures and Solutions, Part 5, Colligative Properties. In this video, we will qualitatively predict and explain trends in the freezing points and boiling points of solutions. Have you ever wondered why people often add a little bit of table salt to get their water to a boil when cooking up some pasta? Or why we throw salts like calcium chloride on ice on our sidewalks and it melts the ice? Or why rock salt, which is sodium chloride, is necessary whenever you make homemade ice cream. If you've ever wondered about any of that business, well, stay tuned. Recall that an electrolyte is any substance that will conduct electricity when dissolved or melted. Ionic compounds are considered electrolytes because they will conduct electricity when dissolved in water. This is because they will dissociate into individual ions. These charged particles can freely move around and carry electric current throughout the solution. The submicroscopic view on the left shows the ions of dissolved sodium chloride, which can conduct electricity. The submicroscopic view on the right shows the dissolved molecule of sucrose, which doesn't dissociate into ions in solution. Covalent compounds remain individual molecules, which aren't charged when they dissolve. Since there is no dissociation, there are no ions, and the solution on the right cannot conduct electricity. Sucrose is a non-electrolyte. A substance that produces many ions in solution is called a strong electrolyte. Strong electrolytes, like ionic compounds and some acids, will completely dissociate in solution. A weak electrolyte doesn't completely dissociate, so it doesn't produce as many ions. The only weak electrolytes we'll consider in this course are weak acids, but we'll discuss those at a later date. When a strong electrolyte dissolves, it produces a different number of ions depending on how many ions are in one formula unit. For example, each formula unit of sodium chloride will dissociate into a sodium ion and a chloride ion. So for every 1 mole of NaCl, there will be 2 moles of ions in the solution. Calcium chloride has 1 calcium ion and 2 chloride ions per formula unit. So for every 1 mole of calcium chloride, there will be 3 moles of ions in the solution. What do you think? How many moles of particles are in a solution when 1 mole of sucrose dissolves? It's 1 mole. Sucrose is a covalent compound. It's a molecule, so it doesn't dissociate. Sucrose is a non-electrolyte. So for every 1 mole of sucrose molecules that dissolve, there will be 1 mole of solute particles in the solution. This video is primarily about colligative properties, which are the physical properties of solutions that are affected by the number of particles dissolved, but not by the identity of those particles. The word colligative means depending on the collection of. So it makes sense to describe these properties with this term, because these properties will be determined by the collection of particles in the solution and not so much on which particles they are. We'll look at vapor pressure lowering, boiling point elevation, and freezing point depression. For our first colligative property, we'll look at vapor pressure. Recall that vapor pressure is the pressure of the gas that evaporates above the surface of a liquid. Whenever a non-volatile solute, don't worry, that's the only kind of solute we're going to consider in this chapter. Whenever a non-volatile solute is added to a solution, it will always lower the vapor pressure of the solution. That's because the dissolved particles of the solute and their attractive forces make it more difficult for the solvent particles to evaporate. Less evaporation means less vapor pressure. And it only matters how much solute particles are in the solution. The more particles dissolved, the lower the vapor pressure gets. That's vapor pressure lowering. Let's see if we got this. Predict which out of these 3 sets of pairs will have the lower vapor pressure. Don't forget that strong electrolytes will dissociate into multiple particles, and you can assume that we're always talking about aqueous solutions for the solutions. So, what do you think? Which will have a lower vapor pressure, pure water or a sucrose solution? It's the sucrose solution. Remember that adding solute will lower the vapor pressure of the solvent. Sucrose solution has solute in it, but pure water is just solvent. The solution has a lower vapor pressure. But what about the second pair? They're both solutions. Which solution will have a lower vapor pressure? 1 molar sodium chloride or 2 molar sodium chloride? It'll be the higher concentration of sodium chloride solution. More solute particles are dissolved in the higher concentration solution, so there will be more lowering to the vapor pressure. At last, we have 1 molar magnesium chloride and 1 molar aluminum sulfate. Which one do you think will have the lower vapor pressure? No, it's not a trick question. They won't both have the same vapor pressure. These strong electrolytes will dissociate into a different number of ions. Magnesium chloride has 3 ions in the formula unit, so 1 molar MgCl2 will dissociate into 1 molar magnesium ions and 2 molar chloride ions. That's 3 moles of ions per liter. For aluminum sulfate, it has 5 ions per formula unit, so 1 molar Al2SO4 will dissociate into 2 molar aluminum ions and 3 molar polyatomic sulfate ions. That's 5 moles of ions per liter. More particles in solution means the vapor pressure goes down more, so 1 molar aluminum sulfate will have the lower vapor pressure. Now we have another colligative property, and it's called boiling point elevation. When a non-volatile solute lowers the vapor pressure of a solvent, the boiling point is also affected. Since the solvent will not boil until its vapor pressure is equal to the atmospheric pressure, more energy is required to increase the vapor pressure high enough to get the solution to boil. That's because the higher temperature gives more solvent particles sufficient energy to escape to the gas phase. So, whatever causes the vapor pressure of a solution to go down will cause the boiling point to go up. And it's a colligative property, so the more solute particles dissolve, the more the boiling point goes up. So, now do you understand why adding salt to water when cooking pasta is advantageous? Well, actually, that doesn't even make sense now. Adding salt will raise the boiling point, so it will take longer to get the water to boil. I guess at the higher boiling point temperature, the pasta will cook faster, but in reality, we're only talking about a couple of seconds faster. So I guess it's really just to make the pasta taste better. That's why we add salt to most of our foods. But why do we add it to our roads and sidewalks? Surely no one's going to eat the road, right? Right. The reason we add salt to roads and sidewalks is because of the freezing point depression. Just as the solution's boiling point is always greater than the pure solvent's boiling point, a solution's freezing point is always less than the pure solvent's freezing point. The lower vapor pressure produces a lower freezing point because the solute particles get in the way of the crystallization process with the extra attractive forces between the solute and the solvent. And it's a colligative property, so the more solute particles in the solution, the lower the freezing point will go. So when you make the ice on your sidewalk all salty, it makes the freezing point go down. So hopefully it's not cold enough to freeze the ice and it'll stay liquid water instead. So when making homemade ice cream, you can't just use ice because ice is melting at 0 degrees Celsius and that isn't cold enough to freeze the milk. But with salty ice, it melts at about -10 degrees Celsius, and that is cold enough to freeze the milk into ice cream. Yum. Here we see in the dotted red lines how the aqueous solution's vapor pressure decreases from the pure water. That lowering of the vapor pressure lines will end up with a freezing point shifted to the left, so a lower temperature at 1 atmosphere. And it ends up with a boiling point shifted to the right, so a higher temperature at 1 atmosphere. Vapor pressure lowering leads to a lower freezing point and a higher boiling point. It basically expands the range of temperatures that'll keep the solution in the liquid state. Now let's take a look at 3 solutions here and try to predict which one has the lowest freezing point. Assume these are all aqueous solutions except for the pure water, that's just water. So, which one has the lowest freezing point? It's the 2 molar sodium phosphate that will have the lowest freezing point. That's because each formula unit of sodium phosphate will produce 4 ions. So that will be 8 molar ions in the solution. That's more than the 6 molar ions you get from 3 molar sodium chloride and is certainly more than the 0 particles dissolved in pure water. More solute particles means more lowering of the freezing point. Now let's see if you can list these 4 solutions in order of increasing vapor pressure. Part 1 here. One molar aluminum chloride gives us 4 molar ions, which is more than the 2 molar ions we get from dissociating 1 molar NaCl. And that's more than the 1 molar of molecules we get from a 1 molar sucrose, because that's a non-electrolyte. But it's still more than 0 molar stuff dissolved in pure water. So the more stuff dissolved in the solution, the lower the vapor pressure will be. So now rank them in order of increasing boiling point. We'll reverse the order for the lowest to highest boiling point, because the more the vapor pressure goes down, the more the boiling point goes up. Water has the lowest boiling point because it is the pure solvent. Aqueous solutions with non-volatile solutes will always have a higher boiling point than pure water. And the more solute particles there are to dissolve, the higher the boiling point will go. So, what about part 3 here? Can you rank these in order from lowest freezing point to highest freezing point? Will it look like the order for number 1 or the order for number 2? It'll match the trend for increasing vapor pressure. More particles dissolved, like in 1 molar aluminum chloride, means more freezing point depression. The more stuff dissolved, the more the freezing point goes down. Water will have the highest freezing point on this list because there aren't any solute particles to lower its freezing point. In this little video, we've qualitatively predicted and explained the trends in freezing and boiling points for solutions. It's been real.